Here's a probability problem that sounds like a 1 in 100 gamble. A full plane has 100 passengers. Passenger 1 loses the boarding pass and takes a free seat at random. Everyone else takes their assigned seat when it is available. What is the chance the last passenger gets seat 100? The exact answer is 1/2. Take a smaller plane to see the mechanism. If passenger 1 takes seat 1, nothing happens. If they take the last seat, the last passenger loses immediately. But if they take a middle seat, only one later passenger is displaced. Passengers before that person still sit normally. Suppose the first passenger takes seat 5. Passengers 2 through 4 sit down. Passenger 5 finds seat 5 occupied, so they choose a free seat. If they take seat 7, passenger 7 becomes the next forced chooser. If 7 takes seat 1, the chain stops, and the final passenger's seat is still free. That is the whole shape of the process. Every interior choice just passes one wrong seat forward. The chain cannot loop forever. Eventually, it must take one of two special seats, the first seat or the last seat. Taking the first leaves the last passenger safe. Taking the last blocks them. Now the key question, why are those two endpoints equally likely? Reverse the entire row. Every legal random run ending at the first seat becomes a matching run ending at the last seat, with the same probability, because all free seat choices are uniform. The pairing swaps winners and losers 1 for 1. So the two endpoint probabilities are equal, and they add to 1. Each is exactly 1/2. The same idea generalizes. If the first k passengers are all absent-minded and choose randomly, there are k plus 1 ways for the chain to end. The last passenger's success probability becomes 1 over k plus 1. One absent-minded passenger gives 1/2, 2 give 1/3. Hens and last prove this broader model, but the one-passenger symmetry already solves our puzzle. I also checked the rule with a deterministic simulation, 200,000 boarding runs for each of several plane sizes. The frequencies stay near 1/2. That experiment checks the implementation. It is not the proof. The exact result comes from the chain and the reversal symmetry. So the last passenger was never making a fresh 1 in 100 guess. A random first seat creates a structured process with two symmetric endpoints that end the chain. Under the full plane, uniform choice rules, the last passenger gets their own seat exactly half the time. Change those rules, and you have a different problem.